Hello everyone, my name is Nayman, and I will present diverse Imagenet models transfer better. This work has been done in collaboration with Avram Golbert, Asaf and Lihi Zelnik-Manor. So let's start with an overview. So in this work, we try to identify and utilize the main factors behind the transferability of pre-trained models to downstream tasks. For this purpose, we propose what we call the filter diversity as a calibration for the Imagenet accuracy to yield the calibrated Imagenet score, or in short, the CIS, for assessing the transferability of models. To this end, we introduce a simple training method that enables the injection of label information into any pre-trained model in a controlled manner. This helps us generate models of different levels of filter diversity and Imagenet accuracy. And thus, it allows us to connect between CIS and transferability, while at the same time, this leads to models with higher transferability. So let's start with a little bit of background and share a common hypothesis stating that the higher Imagenet accuracy leads to better transferability of models. This, for example, was shown by Golbert et al. In a broad study over different downstream tasks and many neural architectures. But on the other end, we also know that self-supervised models typically have lower Imagenet accuracy, while at the same time enjoy better transferability compared to the supervised counterparts. So the intuition behind that is that while supervised models focus on class-level discrimination, SSL focuses on instance-level discrimination. So while supervised models learn meaningful high-level semantic features that are common to instances of the same class, SSL can capture irrelevant low-level features, for example, related to the instance background, because they focus on instance-level discrimination. And to conclude, supervised models learn semantically meaningful features, while SSL learn more diverse instance-level features. So the idea is, why not to combine both in order to improve transferability? The thing is that this indeed has been done before, for example, by Golbert et al., by suggesting a new loss function that involves both contrastive terms and supervised terms. And also Islam et al. Tried to mix different type of losses, both self-supervised contrastive and cross-entropy and supervised contrastive loss, and showed that indeed the mix of supervised contrastive and self-supervised contrastive led to the best transferability over different downstream tasks. But all of those previous work mostly attributed the increased transferability to different measures over the activation maps or the feature representation learned by the pre-trained models. For example, the abstraction of representation learned measured by the central kernel alignment between different layers. So there are those models that have more different feature representation learned by different layers enjoy the higher transferability. Or in another case, the intra-class variations and inter-class variations both shown to be correlated with the transferability. Those measures are all data dependent because those are not intrinsic to the model. And we try to explain this by what we call the filter diversity, which is a more intrinsic property of the model, and we will elaborate on in a bit. But we use this notion of filter diversity as a calibration for the original Imagenet accuracy for assessing the transferability of model. We call the new measure the calibrated Imagenet score because it takes the Imagenet accuracy and calibrates it by multiplying it by the feature diversity. And this shows to be correlated much better with the transferability judged by the graphs in the bottom left, leading from a spearman correlation of 0.74 to 0.93. Also, the bottom right graph shows that compared to other factors proposed by previous work, for example, intraclass and interclass variation, and the CKA, as we discussed, the CIS shown to be the most important factors when measured by the feature importance of the XGBoost algorithm. So we focus here on the filter diversity as a notion rather than on the specific implementation, and show that two different implementations lead to same conclusions. So first, we consider what we call the clustering filter diversity, which is an intrinsic property of the model. We take the weight vectors of the different neural layers, for example, the channels of the convolutional layers, and then we use an agglomerative clustering algorithm that clusters together different filters in the weight space. So as many clusters as we have, it means that the weights are less clustered together, and thus the model has more diverse filters. We do that for every layer for different thresholds and aggregate all the layers together into a single number that reflects the filter diversity of the model. Alternatively, we propose also the spectral filter diversity, which is based on the principal component analysis. So stating that the more variance explained by the fewer principal components in the weight space, the less diverse the filters are. So both the CIS based on both implementations of the filter diversity are shown to be correlated much better with the transferability of the model, whether or not we fine-tune the model or we just use the linear probing. So we come up with a simple way to generate models of different levels of the two factors so that we can study the connection of those factors into transferability. We start with an SSL model of I diversity, and then we inject label information in a controlled manner by freezing the backbone, and once in a few steps, updating the backbone with respect to the gradients, and the classifier is updated in every step, such that it carries most of the burden rather than the backbone does. In this graph, we show that how we inject more and more label information over those trajectories, we get closer, higher in the calibrated Imagenet score in yellow, and thus the transferability with higher circles is increased up to a certain point where it starts decreasing. We measure our hypothesis over 14 different data sets of different number of classes, train size, and domains, and show that there is a sweet spot that balances features learned by the self-supervised and self-supervised learning parts. So at the middle point here of just the right amount of label injection, we have a peak in the transferability of the models, where we balance in blue the similarity to unsupervised model and the similarity to supervised model in orange, measured by the CKA. Indeed, we show that those pretrained models with a moderate amount of label injection in tau equals 4 here yield the best performance, the transfer learning performance, over those 14 different data sets. So to conclude our main results, we suggest a new measure that indicates the transferability of models called the CIS, which is based on the filter diversity of models, and it correlates much better to transferability, and it is shown to be very important